This is grade 11 pre-calc, lesson 50, systems of nonlinear equations. Now, most of the times when we're solving equations, we're going to do it algebraically. It's always easier. But this first example is we're going to look at it graphically. And to do this, you would use like a TI-83 or Desmos or something like that. So we have, excuse me, we have two equations here. We got a linear and we have a quadratic. So to do that, what we would do is if in TI-83, you would plug the formulas in, but you have to rearrange them so they're always based on y equals. So if you look, we rearrange the linear, so it's y equals. We rearrange the quadratic, it's y equals. And then we can plug them into the calculator or into Desmos. So then when we graph them, what you're looking for here is there's your quadratic, right? And the linear here is the straight line. So what you're looking for is you're looking for the intersection points of these things. So basically you're looking for that point right there, and you're looking for that point right there. And to do that on the calculator, you look for intersection points, and you would just use the intersection function. You would find out there's 0, 3 and negative 2, 5. And you can actually see it makes sense. 0, 3 is the one up here on the y-axis, and then the negative 2, negative 5 is over here. So this system of system of equations has two solutions, right? 0, 3 and negative 2, 5. So there's going to be different situations, and you'll see this as we go along. And if you wanted to check these, you substitute them back into the original equations, and let's see x and y and plug them in. Just make sure left side equals right side. Okay, so flip the page, you'll see an actual better example of what we're going to do this algebraically. Determine two integers such that the sum of the smaller number and twice the larger number is 46. So this often confuses people because they read the number, they read the words, and they go, I don't know how to change that into an equation. Well, it's not bad. So what we do is we have s as the smaller number, L as the larger number. Always define your variables right to start with. So look at the first one. The sum, so that's an addition, sum of the smaller number, so s plus twice the larger number to 2L is 46. So that equals 46. Okay, so there's one equation. Now for this system to work, system means two or more equations. So we need a second one. So also the square of the smaller number, s squared, is decreased, subtract, by 3 times the larger number, 3L, is 93. Okay, so here we have our two equations. Now, how do you solve this? Well, there's two methods. There's either substitution or elimination. We're going to use elimination on this one. So what we can do is take the whole top one, times it by 3. Take the whole bottom one, times it by 2. And when I say everything, I'm talking about all the pieces in there. So take the top one, we end up with 3s plus 6l equals 138. Times the bottom one by 2, we end up with 2s squared minus 6l equals 186. Why did we do that? Well, if you look, we have a positive 6l and a negative 6l. If we add those together, elimination method here, those two will disappear. So, okay, let's see what we get. So 2s squared and 3s, you can't add those together. They're not like variables, or sorry, like monomials. So we end up with 2s squared plus 3s equals 324. Okay, this is looking familiar now. This is a quadratic. Bring the 324 over to the other side, make it equal to 0. Hey, can we factor this? Now, if it doesn't factor, you're going to have to use the old quadratic formula, but this one factors in this case. So 2s plus 27, s minus 12 equals 0. So what we do, we set them equal to 0, split each sides. So s equals negative 27 over 2, and s equals 12. Now, go look back at the original question here. It says determine two integers. Integers are either positive or negative whole numbers. Okay. So that's negative 13.5. That one is not an answer. That's an extraneous root. Okay. So this one works, s equals 12, but we're not done, right? Because that's only the smaller number. How do you find the larger number? Well, you plug it into either one of the formulas above. You plug it in, you find L equals 17. So solution in this case, right? That's just the abbreviation for the word solution, is 12, 17. Now, this next example on the third page, it's a really interesting one. It's a real-world example. So what it is a Canadian cargo plane drops emergency supplies on the back. And what it is, it's all based on formulas. So what happens is they throw the emergency supplies out of the plane. After a certain amount of time, the parachute opens, and then it lands in a certain spot. And it's all based on formulas. So here's the height of the crate during free fall, and that's quadratic, right? Because the plane's moving as it's coming down, right? And this one represents linear because once the parachute opens, it's almost a straight line to the ground. So they can actually use these formulas, not these specific formulas, but they can use formulas to predict where things will land on the ground. I think you usually get it within quite a few meters. So what we do is we have the two formulas. Now, if you look, they're both equal to h. So what we can do is we can substitute, instead of elimination, which we did on the last example, we use substitution on this one. They both equal h, therefore they both equal each other. So this negative 5t plus 650 equals negative 4.9t squared plus 700. You can see that's what we did right here. Because they both equal h, they both equal each other. Okay? So then you work through this and you get this quadratic form. Now, you get this quadratic. Now, you got to realize right away, you got 4.9 in there. And in the original question, I think it says, no, it doesn't give anything about rounding or anything like that. But the dead giveaway is because it's 4.9t squared, you got to use the quadratic formula. There's no way you're going to be able to factor this. So we know what a is 4.9, b is negative 5, c is negative 50. So take the quadratic formula, plug it into the quadratic formula, do all the math, and just keep working it through, and you find out, okay, x is 3.745 and x is negative 2.724. Now, hey, wait a sec. This should be something interesting, an indicator right here. It's negative. Time can't be negative. Last time I checked, unless you own a time machine, which I don't think exists, you can't have negative time. So if you look at this one, we have 3.745. So that's x in the time-wise. How do you find the height? Well, you plug that into the formula. If you notice, you see I have 3.745 ... because what I've done is I've kept the 3.745 and all the rest of it in the calculator to do all the rest of the calculations. You do that so it remains accurate up to the end. Don't round until the end. So h equals 631 point, all the change here, or 631 meters above the ground. To verify, you just plug it into the first equation. So there's a real-world example of using quadratics and using systems of equations. Now, in reality, they would probably do this with a calculator, but we're doing it manually because we love math so much. Okay, go to the last page. Last example, solve the following systems of equations and verify your solution. So what we got here is you got to look at this one. First off, you might have to rearrange stuff. The x squares are not bad. The x's are lined up and the y's are lined up. So this 4, it's on the wrong side. You can either bring the negative 2 over or the 4 over to this side. I brought the negative 2 over onto the other side of the equal side. So make sure it's in a proper format. Now, if you look at this, I need to not add these ones, because if I add these ones, that's not going to get rid of the y's, but I'm going to subtract them. Now, if you look, I'm trying to get rid of the y's. That's usually your indication. When you have x squares and x's and y's, try to get rid of the y's, because then you end up with a quadratic all the time. If you were able to get rid of the other stuff, you'll end up just with an x and y, and just a linear. Okay, so we subtract this out. Now, you got to be careful when you're subtracting. That subtract goes with everything. So it's 3x squared subtract 6x squared, negative 3x squared. Then it's negative x subtract positive 4, which is negative 5x. Then it's negative y subtract negative y, they eliminate. 2 subtract 4, which is negative 2. Now, don't make that mistake, right? That subtract goes with the whole thing. If you have trouble, you could do addition, but then you'll just have to change one of these things. Like you could either change the bottom one by multiplying by negative 1 or something like that. I think that's what I did down. Oh, no. Okay, so then we have our quadratic. Bring over the negative 2. Now, interesting thing is I don't like the negative 3 in front of it because I like my a value or my front value to be positive. So I can multiply the whole thing by negative 1. You can do that as long as you multiply everything by negative 1. So what happens is it basically changes all the signs. So we end up with 3x squared plus 5x minus 2 equals 0. Does this factor down? Yes, it does. Factors into 3x minus 1, x plus 2. Again, solve it. So we have x equals 1/3 and x equals negative 2. Now, should you check? Well, of course. But before you check, let's substitute in. So we got to substitute in x equals 1/3. And you can substitute into either equation. It makes no difference. Because it's, remember, you're trying to find the intersection point of two equations. So it's going to be the same for either equation. So we plug in a third, and we plug in negative 2. I did it backwards. Okay. So we plug in negative 2, we get y equals 12. We plug in 1/3, we get y equals negative 2. So we have two solutions in this case. Negative 2 comma 12 and 1/3 comma negative 2. Right? Does that make sense? Give those a shot now.